Hi, we're Group 7, and for Embedded Systems Design this semester we built a mini autonomous robotic vehicle. I'm Alex Corvin.
I'm Stafford, Worrell.
I'm Jackie.
And I'm Kausch.
For this project, we were given a set of requirements. First, we had to be able to wirelessly connect to our rover to issue any set of commands. The rover had to be able to complete straight line motion, L-shaped motion, and finding the cube. Finding the cube, there'd be a set of 6-inch cubes in a room, one of which we've built, and we had to be able to find it. We needed to be able to do this both with and without obstacles in the room. For L-shaped motion, we were to implement driving forward some distance, turning either left or right, and then driving a second distance. For straight line motion, we were to just simply drive forward for a specified distance. Each group for this project was given the Lynx Motion Rover kit, a set of PIC processors, and an ARM processor. In addition to that, we had a $400 budget with which to buy sensors or any other hardware that we needed. Finally, we were to implement some optional tasks that we were to come up with, and for this we've decided to implement remote-controlled operation of our rover. In our design, we decided to mount the ARM processor directly on the rover. We did this so that we would be able to minimize the amount of data that was sent wirelessly from the ARM processor to the PIC processors on the rover. This required us to have a robust means of connecting wirelessly to the rover, so we decided to implement this using a Pico Station wireless access point. This gave us a reliable connection which could be reached from great distances. When we connected to the Pico Station, we were able to browse to the website running on the web server. On the web server, we had pages that allowed us to input parameters for each run mode. There was a page for straight line motion, L-shaped motion, find the cube mode, and remote control mode. Whenever the parameters were filled in and submitted to the web server, they were parsed and passed into the message queue, which then interrupted the navigation task. When the navigation task was interrupted with a set of these commands, it parsed the commands and started each appropriate task. If there were obstacles present, the mapping task would be started. If we were to find the cube location task was to be started. And otherwise, if we were to calculate a motor command and send it to the motor command thread. My task was to implement the navigation thread as well as the web server. The purpose of the web server was to provide an interface to connect to the rover and issue it commands for how to operate. And the navigation thread acted as the linking point between each of our activities and generated motor commands to be sent to the motors. Information about where to go next is sent to the navigation thread from one of two places. It could come from the cube location thread or from the mapping thread. When it comes from the cube location thread, the navigation activity receives an angle to go to reach the cube. From this, commands are sent to the motor command thread, subsequently in 5-degree increments to turn towards the cube. Once we get within 5 degrees of the angle towards the cube, I send a command to start going towards the cube until I get a new angle from the cube location thread. When a command comes from the mapping activity, the navigation thread receives information on the rover's current location as well as the destination location. From this, the optimal path to take is calculated using Dijkstra's algorithm, which involves calculating the path of least cost between the 2 points. Once the path is known, motor commands are generated and sent to the motor control thread. Once the navigation thread determines the next location to go to, a command must be generated to be sent to the motor command activity. These commands can take the form of either a command to drive forward or backwards some distance, or a command to turn left or right some angle. Because our API for sending motor commands uses a multi-byte format, we were able to send commands to drive forward or backwards a very large distance when necessary.
So I'm AJ, and for my part of this project, I was responsible for the motors and the drivetrain of the entire system, and how to calculate how far we have moved. The drivetrain is composed of 4 motors mounted inside our little rover here. We have 4-wheel drive. We steer with a tank drive system, So in order to turn to the right, we spin the left wheels forward and the right wheels backwards. We also are using a motor controller, a saber tooth. It's mounted inside the base unit, and it connects to this pick right here via a UART connection. This UART is a 9600 baud rate. The encoders, we use motor encoders to track how far we have traveled. There are two encoders mounted on the front wheels, left and right. These encoders connect into interrupt-driven pins on the pick board. We generate an encoder interrupt. You can see these lights right here are just saying, hey, we have an interrupt going off right now, and we increment a value for these. So I calibrated the encoder so that essentially 415 essentially interrupts, little pulses generated by spinning the wheels, corresponds to 1 inch. We were able to, in straight line motion, move almost precisely whatever amount we could punch into the web server. To find the cube mode, we were required to move various angles. To accomplish this, we implemented a 5-degree turn to the left or right. That way, we could essentially move any direction we needed to very accurately. We were able to find the cube by moving with our 5-degree angle turns, just one followed by the other. And we accomplished this task in approximately 10 minutes. In our straight line demo, we were asked to move 10 feet. With the encoders calibrated, we came up just short. We were 2 inches short in the straight line movement. In the L-shaped demo, we were asked to move 5 feet forward, turn right 90 degrees, and then move another 5 feet. In this demo, we also came up 2 inches short.
Several of the objectives we were required to complete required the rover to know whether or not there were obstacles around it and navigate around these obstacles. To facilitate that, I designed a turret, which you can see mounted here on the rover. The turret uses a Dynamixel AX12 servo to scan a IR rangefinder back and forth in front of it. As the pick is continuously sampling these values from the turret, a task on the arm is requesting regular intervals over I²C to get these values. This sensor task then takes the raw values, converts them into sane things, so as opposed to just a voltage from the IR sensor, it uses linear interpolation to obtain an actual distance measurement. This also occurs for the servo angle, which is just given as a straight position. The sensor task on the arm itself is implemented as a finite state machine. In its initial state, it has no new data, so it sends out these I²C requests. It then transitions to the next state, the data acquisition state, where it is waiting for all the values to come back in. And once it has all these values, it transitions to the final state and uses that state to fire off a message through a message queue to mapping with all these updated values. So unfortunately, we ran out of time to fully test this, but once the map was fully updated with new sensor values, the mapping task was supposed to send a message to the navigation task informing it that it should scan through the map and update its trajectory accordingly. There simply wasn't enough time to debug all the minor little things with that, so we weren't able to complete the obstacle avoidance challenges. However, we were able to demonstrate the internal map updates through the use of the LCD, displaying the cell values on the LCD as it updated. The IR sensor on the turret is sampled using the PIC's ADC at regular intervals. In fact, the PIC is continuously scanning the turret back and forth and sampling. As you can see, the map that the rover currently has stored is displayed on the LCD. And since there's nothing in front of the rover, there are no points displayed. When I place an obstacle in front, after a certain point, the threshold is reached and the cell is displayed. As objects disappear from the rover's field of view, the corresponding cell values are decremented to reflect this change. This can be demonstrated by removing the obstacle and observing that over time the cell values disappear.
To handle locating the cube, we wanted to go with a triangulation system that could calculate the angle towards the cube. And to do this, we put a speaker on the cube and 3 receivers on the sensing system. We have an ultrasonic emitter on the cube, which is driven by a PIC processor, which generates a 40 kilohertz square wave. You can see when this yellow light is on, there's a 40 kilohertz square wave being generated. When it's off, there's nothing. So this sends out a blip about once per second. The output of that goes into a MOSFET driver, which we use to amplify the voltage to get a stronger broadcast from the system. We have 3 receivers on the rover. The back one currently isn't working, so we use the front 2. And these receivers are made up of 4 microphones, which feed into a 2-step amplifier, a high-pass filter, and finally a voltage comparator. And the voltage comparators thresholds can be adjusted with these knobs. We also have a knob here to adjust the sensitivity of the proximity detector, which this sensor doubles as. And that tells us when we're close to the cube. You can tell it's working by the green light that lights up down there. I don't know if you can see that. When the cube gets too far away, that doesn't light up. These blue lights here light up every time a signal is received. The outputs from the comparator circuits feed into this PIC processor, which uses a capture mode to accurately time the difference between when the sound wave hits this receiver and when it hits this receiver. From that, we can calculate an angle towards the cube. These angles aren't always accurate, so the way we handle that is we take 10 readings and take the median of that. We also account for variance in each reading, and if the variance is too high, we conclude that there's no reading. And that gets sent to the navigation task, which either performs some random walk if there's no reading. If there is a reading, it turns to that angle and heads straight, and then waits for a new reading.
For our optional requirement, we decided to implement a radio-controlled setup. Essentially, we have the web server. We added 5 buttons to the web server, essentially for forward motion, left turns, right turns, reverse motion, and a stop button. There's a Perl script that does an HTTP GET on these web pages and allows us to control the rover by essentially just hitting the button. We used an Xbox controller plugged into a PC, and we calibrated the joystick as well as the D-pad to interpret these commands. On the motor side, essentially as soon as the motor gets a motion, the motor controller gets a motion to move forward or to the left or to the right, it gets sent from the web server down to the arm over using the Pico station. The arm then sends a command to the PIC processor, which it gets interpreted, the motor command gets interpreted, and gets sent to the motor controller via the UART.
Scale for